The second fundamental theorem of calculus is closely related to the first fundamental theorem of calculus. Now remember, the first fundamental theorem of calculus said that the integral from a to b, where a and b are constants, of f of x dx is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. The second fundamental theorem of calculus involves defining the antiderivative as the integral where one of the limits is a function of x. Now, f of t is a function of t, and t is our dummy variable, and you're going to see why we use it in a minute. The second fundamental theorem of calculus tells us if f is continuous in an open interval containing a, then for every x, the derivative with respect to x of the integral is a function evaluated at x. Now, let's use the second fundamental theorem of calculus to calculate the integral from 0 to x of t squared plus 1. You see that we're taking the derivative, so it's going to be this function evaluated at x. Now what if we have something like this? F of x is equal to the integral from pi over 2 to x cubed of cosine t dt. Let me make a substitution. This is not x, so I can't use the fundamental theorem directly. So what if I let u equal x cubed, and du is 3x squared. Then I can write this as a function of u is equal to the integral from pi over 2 to u of cosine t dt. So if I wanted the derivative of f with respect to x, this is going to be the derivative of f with respect to u times the derivative of u with respect to x. I got my dx there, sorry about that. So I have du dx. What is the derivative of f with respect to u? Well, that's the integral from pi over 2 to u of cosine t dt, and I'm taking the derivative with respect to u of this. I can use the second fundamental theorem of calculus, and this is just cosine of u. So if I want d of f dx, I need the derivative of f with respect to u, which is cosine of u, times the derivative of u with respect to x, which is 3x squared. Now I can't have mixes here, so this is 3x squared. The cosine of u is cosine of x cubed. Now you're going to see in general that the derivative with respect to x of the integral of a function, say, let me just do one. Say from a constant to some function, g of x of f of t dt. If I take the derivative of this, it's going to be f evaluated at g of x times the derivative with respect to x of g of x. Now, what if I'm trying to take the derivative with respect to x of the integral from, let's call this h of x down here, to some constant b of f of t dt? Well, remember we always subtract off the lower limit, so this is going to be f evaluated at h of x, and the derivative of this is going to be minus, because we're going to be subtracting this, dh. Now we can get really, really wild. What do you do when I want the derivative with respect to x from the integral of h of x to g of x? So these can be completely independent functions of f of t dt. Well, this is going to be f evaluated at g of x times g prime of x minus f evaluated at h of x times h prime of x. Have this written in your notes for class.